Hello everyone, and welcome to our Vietnamese Chemical Association webinar in August. And as you may know, the Vietnamese Chemical Association is established to seek and connect Vietnamese professionals at all levels and in all fields of the chemical science and engineering all over the world. And with that, we are honored to receive the sharing from Professor V. Dong from University of California, Irvine today. Professor V graduated from UC Irvine when she majored in chemistry and completed an honor degree, an honor project with the Larry Overman. And after graduation, she joined David MacMillan group at UC Berkeley and then moved with his group to Caltech to complete her doctor's studies. Professor V pursued training in organic metallic and supramolecular chemistry with Robert Overman and Kenneth Raymond at Berkeley, and she began independent academic career at University of Toronto, where she was promoted with tenure and named Adrian Brook Professor. And after 6 years in Canada, Professor V returned to the United States to assume the professorship at her alma mater, UC Irvine. And Professor V. Dong research group is interested in new reaction methods, enantioselective catalysis, and natural product synthesis. She has been awarded the ACS EJ Corey Award and is currently an associate editor for chemical sciences, and she also award many others awards. And today, Professor V will talk with us about ruthenium and cobalt catalysts for use in enantioselective hydrofunctionalizations. And before starting Professor V's talk, I would like to ask you to please mute your microphone when Professor V is talking so the lecture will run smoothly. Thank you for your cooperation. And now I would like to Professor V to start the talk. Thank you. Cobalt catalysis.
Great. Thanks so much, Nhan, for the very kind introduction. Trước hết, mình xin cảm ơn VCA cho cơ hội có mặt hôm nay. Tất cả chúng ta đều có chung sở thích về hóa học, tuy nhiên chúng ta cũng có chung một ngôn ngữ ẩm thực, lịch sử và văn hóa. Hôm nay mình sẽ chia sẻ công việc của sinh viên mình về việc phát minh ra các công thức biến đổi mới, hy vọng dùng hóa học để xây dựng một thế giới tốt đẹp hơn cho con em của chúng ta trong tương lai. So with that, let me share my screen. Yeah, so just to reiterate, I wanted to thank Khan for this invitation and the VCA for the opportunity to be here with all of you today. It's really exciting to connect with other chemists who not only share a love of chemistry, but also a common language, history, and interest in food and culture. And so what I'd like to do today is share my research team's interest in developing new transformations for organic synthesis. Our goal really is to develop technologies that result in a more green and sustainable future for the children of tomorrow. And so because this is a lecture on Zoom, I know some of you are joining here today on Zoom, many of you are via Facebook. I thought I'd try to make it a little bit interactive and ask you for some feedback on not only your favorite chemical reactions, but some of your favorite Vietnamese dishes. So Khan, since you're our host today, and Nhan, if you don't mind, maybe you guys could share what are some of your favorite Vietnamese foods and maybe things that we should all think about trying for dinner later.
So I did try to create the poll online. Not sure, Nhan, can you check to see if the poll is on? I asked people what's their favorite Vietnamese dish, and I have to give them options. So I put bún riêu, phở, bánh mì and cơm sườn on there. But,
Those all sound good.
yeah, mine is obviously bún riêu and cơm sườn, basically.
Nice, nice. What about you, Nhan?
Mine is bánh mì. Yeah, maybe that's my favorite food. I could eat it like in the morning or in the evening. So
All right, awesome. Yeah, and anyone joining on Zoom, feel free to vote for your favorite Vietnamese food today as well. And so I think in some ways, chemical reactions might be like our favorite foods, right? Everyone has their own particular favorite. And it might have been some reaction that you learned about when you were a student learning about chemistry that really sparked your interest in this field. And so our group also wanted to ask this question, what are our favorite metal catalyzed reactions? And so I know you're a biophysical chemist, but do you have a favorite organic reaction that you sort of are inspired by?
Well, I think back then I did try organic chemistry at some point, and amination was what I attempted to do. But
Okay.
I don't know a lot about organic reactions anymore.
Okay, yeah, that's a great reaction, right? Making carbon-nitrogen bonds, because those are so common in medicines. What about you, Nhan?
because my major is organic chemistry actually, and I work on the nickel catalysis, enantioselectivity, and I work focused on the aldehydes, and that's in my favorite because like from that can go further more transformation, something interesting.
Yeah, that sounds great. And nickel is a really important metal catalyst right now, right? In terms of cheaper, sustainable metals. So
On,
thanks a lot,
on
guys.
Facebook, I can see right now someone said that sonogashira is also is a favorite reaction from Yangjin.
Okay, great. The Sana-Gashira cross-coupling is a really powerful transformation. Yeah, so feel free to share on Facebook or comments on this question. When we thought about this question, we decided that to some ways we can kind of cheat and choose these three transformations that have already won the Nobel Prize in organic chemistry, right? So palladium cross-coupling, asymmetric hydrogenation, and olefin metathesis. And so when my group started up, our research team, we thought, could we learn from these three Nobel Prize winning areas and combine the features, develop chemistry that was atom economical, so there's not much waste generated. You take starting materials and all the atoms end up pretty much in the products. The other goal was to develop asymmetric chemistry, so similar to asymmetric hydrogenation, to be able to set stereocenters containing carbon-hydrogen bonds. And then in the same way that metathesis uses simple building blocks like olefins, we wanted to focus on unsaturated building blocks. And so like cross-coupling, the goal is to bring these two things together in an asymmetric fashion. So at the center of this Venn diagram, my group thought would be metal-hydride catalysis. And so I do have one more question for the audience today. And actually, this is a poll that was also conducted on Facebook earlier, so we can also compare the results there. But the question is, what would you like to hear about? So the title of our talk is Choose Your Own Adventure. And I'll tell you a little bit about each area. So my group has had a long-standing interest in using the metal hydrides generated from the activation of an aldehyde CH bond. And so we're interested in adding these to carbonyl compounds, to olefins. We discovered by accident a way to extrude CO and hydrogen and dehomologate to make alkenes as well. And so I think my group is most established in this area. And in this talk, I can give you kind of like a historical perspective of the field, what we've been doing in it in the past, and what directions we're taking in the future. Another area that's relatively new for our lab, it's along the same idea of using metal hydrides and adding to olefins, but here we expand the scope. And so we are looking at generating metal hydrides that will react with a wider range of nucleophiles. So Kan mentioned amination. We're interested in adding amines to olefins, dienes, and alkynes. We're interested in making carbon sulfur, carbon phosphorus, carbon oxygen, a lot of different kinds of CX bond formations using this hydrofunctionalization method. And then I mentioned hydrogenation is an important area of research. I would argue that it's still a very active area and has a lot of opportunities. And so my students and I have been interested in using cascade hydrogenations to access challenging structures. We're also really interested in using hydrogenation in tandem with other kinds of transformations, such as epimerizations or sigmatropic rearrangements. And in this way, we can generate molecular complexity very quickly in a one-pot sort of tandem catalytic fashion. Okay, so those are the three choices in metal-hydride catalysis, and I'm happy to talk to any of these. And kind of thanks so much for kind of last minute putting together a poll and trying to figure out how to help the audience get engaged in this. So I don't know if you want to go with the Facebook poll that you conducted or the poll today. I'm happy to do whichever.
Yeah, so if we take the sum, let's do that. So the poll conducted yesterday showed that there were 49 people that prefer hydroacylation, 35 hydrogenation, and 26 hydrofunctionalization. It seems like hydroacylation is the favorite one, but for in today's poll, we can see that hydrofunctionalization is actually winning with a total of 12 votes live right now. But still hydroacylation, because of yesterday's poll, is still the winner. So I guess hydroacylation won the gold medal. and silver and bronze will be hydrofunctionalization and hydrogenation.
Okay, great. Thanks. A very good and timely analogy. So yeah, let's talk about hydroacylation today. Thanks everyone for voting and participating in the poll. So it looks like hydroacylation sort of got some extra votes there at the end, so.
Yeah.
All right. So why hydroacylation? When we think about the reaction that's done with homogeneous catalysis on the largest scale in industry, that is a hydroformylation reaction, so also known as the OXO process. In this transformation, one can take carbon monoxide and hydrogen gas, add it to olefins, and make aldehydes, either linear aldehydes or branched ones. And so in our mind, hydroacylation is pretty similar. You can now take these aldehydes in principle, activate the aldehyde CH bond, and add this to an alkene using, again, transition metal catalysis. And so there's also the opportunity to make linear or branched ketones, and these are valuable intermediates that can be transformed to a wide range of products. And so I think the thing that I really sort of was inspired by was this idea that you can combine a CH bond activation with a CC bond formation. And many research groups around the world have been interested in this topic. There is a few names here, and two of my students, Kevin Goh, who's at UC Riverside, and Diane Lei, who's now at Merck as a process chemist, wrote a chapter in organic reactions, kind of detailing every example of hydroacylation. And so one thing I would like to point out, though, is that there's still no real industrial application of this methodology, even though it looks great on paper. And so I'll share some of the challenges in this transformation and some of the opportunities for future development. So before we begin, one thing that our lab likes to do is really take a look at the mechanism before we think about how to develop these reactions. And this is the general mechanism for the hydroacylation. So a metal catalyst like rhodium-1 will engage an aldehyde in an oxidative addition, generating a rhodium-3 hydride intermediate. And from here, this can decompose where you form a rhodium carbonyl complex and then an alkane, or an olefin can coordinate and one can get insertion and then reductive elimination to form the new CC bond. And so there's the challenge of making the linear versus branch products. There's also the challenge of overcoming these side reactions like decarbonylation. And so to address this area, early on in the field, most researchers used directing groups. There were a couple of reasons for this. One, the idea that the directing group would help direct the CH bond activation. And so it was kind of thought maybe that's the challenging part of this transformation. We've later learned, though, that these heteroatoms can also help prevent decarbonylation, so prevent carbon monoxide deinsertion, and then actually funnel this and promote the desired reactivity. Most of the work in this area had focused on making linear products. And so these are achiral products. They're very useful. At the same time, when my group became interested in this area, we really wanted to develop variants that could generate the branched products with the opportunity of making enantioenriched structures or mixtures. And so with that in mind, I wanted to point out here, this is kind of a summary of what we've done in the area. One of our very first hydroacylations was an intramolecular version where we incorporated the heteroatom. And so this allowed us to make medium-sized cyclic ketones with high enantiomer control. We also developed a version where we took cyclopropenes and used ring strain to drive the desired reactivity. My students also incorporated directing groups onto the olefin component itself. And so in that case, we could direct for the branched products. And so we found that sulfur, oxygen, homoallylic and allylic alcohols are both possible. And then by further tuning the catalyst, we ultimately found that we could also generate these products without any directing group on the alkene component. And so I should point out, since we're at the VCA, this work on cyclopropenes was done by one of my very first Vietnamese PhD students, T. Phan. And this chemistry on the simple olefins was done by Christine Lee, who's now a professor in Canada at, I think she's at York University, and she was also a previous speaker here. So Christine completed this work as a master's student. So I guess like in terms of the hydroacylation, one of the things that my students did, we were really interested in was, can we develop the analogous reaction where instead of a carbon-carbon double bond, we basically replaced that with a carbon-oxygen double bond. And so this resulted in really the first kind of early examples of enantioselective ketone or carbonyl hydroacylation. So I'm just highlighting some of the examples here. First, we developed intramolecular versions to make medium and also 5-membered rings. We could expand this to larger rings using nitrogen as a directing group. Kevin and Diane developed an intermolecular example where we take an aldehyde and a ketoamide and generate this DEPC peptide linkage with high enantiomer control. And then Ziwei and Song demonstrated that we could also desymmetrize to make these bicyclic ring systems, setting a quaternary carbon center. And Ziwei and Song went on to show that this was a valuable intermediate in the total synthesis or formal synthesis of a natural product called mesembrine. And so with that in mind, I wanted to sort of give that background and then spend some time telling a story about how nature activates aldehyde CH bonds and what this led us to develop next. And so in the biosynthesis of cholesterol, this is something that's happening in plants, animals, in humans. There is a step involving an oxidation to an aldehyde and then a deformylation where the aldehyde CH bond or the aldehyde is activated and one generates a carbon-carbon double bond and extrudes the equivalent of carbon monoxide and hydrogen, in this case in the form of formic acid. And so what we were interested in was, would it be possible to develop a synthetic version of this transformation? So could we take aldehydes? Now, instead of doing the hydroacylation that I summarized earlier, or instead of the decarbonylation, we wanted to divert this organometallic intermediate to a completely new basically process where we would extrude carbon monoxide and hydrogen and add those components to a strained olefin. This would result in an alkene that now has one carbon less, and then this sort of byproduct aldehyde. And so this was the key question. When we thought about this, really, why would this be possible? We really had to depend on two factors: tuning the bidentate phosphine ligand or tuning this counter ion X. And so it turned out that the nature of the counterion was very critical. So just as an example here, this is our model system. And you can see here that traditional counterions, especially non-coordinating ones, led to no reactivity. But when we switch to a very coordinating counterion, this benzoate, we see 99:1 selectivity for the carbon-carbon bond breaking reaction at 90 degrees in an hour. And this was pretty mild. We don't see any isomerization of the alpha olefin. Now, when Stephen switched to more strained olefin acceptors, so this derivative here, it's a very strained derivative of NBE, we can actually break these carbon-carbon bonds at room temperature with 99:1 selectivity. So this was a really exciting result in the lab for us, just the idea that we could extrude CO and H2 under such mild conditions at room temperature, generate these alpha olefins. And so the team went on to show some of the scope that could be achieved using this new dehomologation. One application was to test it in the synthesis of a natural product called yohimbinone. So this is a natural product that's been made in 10 steps before in racemic form by Al Padwa's lab at Emory University. So Stephen was able to demonstrate a very short 3-step synthesis involving a natural product that's readily available. So this is a really inexpensive natural product that we could buy called yohimbine. So a reduction followed by an oxidation to the aldehyde, and then the transfer hydroformylation results in yohimbinone. So that work was published early on in 2015. And since then, my research team's been really interested in further investigating this kind of transfer chemistry. So I wanted to point out Professor Nozaki's group in Japan, and also she developed an iridium catalyzed version shortly after ours, where they were also able to turn aldehydes into olefins. And then Bill Morandi's group has really demonstrated a lot of examples of this shuttle catalysis, where one can transfer simple functional groups and shuttle them between, in this case, between olefins. And so I want to take a step back. Let's look at this cascade I mentioned earlier again. What we were interested in was, could we go a step back and take an alcohol and then have this undergo an oxidation deformylation? So a cascade process where we can now dehomologate alcohol substrates. And so ultimately what we found was this is possible if we use the right acceptors. And so earlier I talked about this very strained NBE acceptor. Here, if we move to acrylamide as the acceptor, we see formation of the desired product in this cascade fashion. And so Fabian and Alex worked together to demonstrate that the byproducts of this reaction were the actually reduced alpha beta saturated Michael acceptor to make this amide, and then carbon monoxide in this case is a byproduct. So this is mechanistically very different from what I just presented before. We don't see incorporation of CO into the sacrificial oxidant. And in this case, we actually see carbon monoxide generated. So one of the things that I like to do as an undergrad was actually these dehomologations en route to a substrate I was making. And so I think this offers an interesting way to take dodexine, for example, through a very simple hydroboration, make an alcohol, and then one can turn it into undexine, right? An olefin with 1 carbon less. And so this gives an opportunity to shuttle carbon feedstocks that might not be readily available into other forms. We can also perform a 2-carbon dehomologation. So in this case, a dihydroxylation followed by 2 dehomologations or transfer hydroformylation reactions results in dexine. So our group's interested in furthering this work. Right now, we are very interested in understanding the mechanism in more detail. And so what we found so far is the alcohol oxidation is actually slower than the aldehyde dehomologation. And perhaps not surprisingly is more sterically hindered substrates react much slower. Benzylic substrates also react faster than our aliphatic ones. Okay, so I'm going to sort of summarize a little bit here. I'd be happy to answer more questions about this work. Some of the areas that we'd like to pursue next involve using cobalt instead of rhodium for these transfer reactions, and and also using less expensive olefin acceptors. And so we're especially interested in ethylene as a reagent. And we have some exciting results showing that by using excess alkenes, we can also drive these equilibrium processes. So we've been talking about aldehyde CH activation. Another reason why we're really interested in aldehyde CH bonds is because of this opportunity to develop new kinds of cyclizations. And so if we think about how nature can take a single starting material like this allylic phosphate, and through cyclase enzymes can fold this into these chiral structures. So saponine, limonene, pinene, camphene all come from the same starting material. In this case, we can see that it's possible to make 4-membered rings, 5-membered rings, and 6-membered rings using catalysis. And so my group is really interested in this question. Can we do divergent synthesis using catalysis in a similar way? So can we take a really simple diene? You can make this in some cases in one step from an aldehyde bisalylation developed by Ben Liss's lab. And so what we found is that, yes, by tuning the metal and the ligand, we can have this undergo an oxidative addition and then cyclization to form cyclopentanones. So this is pretty sort of well established. In this case, what we found that was unique was we could generate these quaternary carbon centers because the olefin acts as a special directing group. And it's actually an asymmetric isomerization that's responsible for the enhanced enantioselectivity. By switching the metal and the ligand around using the right ligand, we can get this to funnel to now a very rare cycloisomerization to make a cyclohexene product. And the reason why I was excited about this is because it represents an alternative to the Diels-Alder 4+2 cycloaddition. And in fact, you can't actually make this particular stereochemical relationship using a 4+2 cycloaddition. By now switching the rhodium out for cobalt, one thing that we found was that we could isomerize now or achieve a cycloisomerization to make a 4-membered ring, a cyclobutanone with high enantioselectivity. So this is a really rare example of a 4-membered ring formation using hydroacylation. And most recently, we've also found that we can also generate bicyclic ring systems by, again, just tuning the metal and the ligand. And so what we're really excited about in this area is the idea that we can really now study this divergent synthesis by catalysis and better understand how to design ligands and how to basically influence selectivity by simply tuning a metal and a ligand scaffold. And so when we think about how that's relatively simple, right, compared to nature's structures, but again, it's sort of surprising to me that you can still diverge in this way. And so we do have a paper that's going to be coming out hopefully sometime soon, where we demonstrate that the way that these metal and ligand catalysts work is not so different from nature, and it really is an induced fit mechanism that is operative here. Okay, so what else do we want to do with these aldehyde CH activations? Well, one thing I really appreciate by the VCA, I was watching your recent lecture on YouTube about opportunities in the biopharmaceutical sector. And so for a lot of the young students thinking about future careers, a lot of medicines that are prepared in industry also use what's called a dynamic kinetic resolution via usually hydrogenation. So in a hydrogenation, you're epimerizing one of your stereocenters and then able to select out to generate products that now bear 2 stereogenic centers. And so I think this is really interesting as an approach for making enantiopure building blocks and also drugs. And so you can see that this has been used in industry for a wide range of products. What my group was interested in was, could we combine this type of dynamic kinetic resolution, right? Use catalysis to selectively transform one enantiomer, but combine this with a CC bond forming reaction like hydroacylation. Okay, so this is the basic idea. Here we want to take a racemic aldehyde, have this undergo rapid epimerization between the 2 enantiomers, and then use a rhodium catalyst to selectively activate one enantiomer that will then undergo hydroacylation to form the cyclopentanone. And so what's unique about this is we would be able to generate 2 stereocenters in a single operation. So this is work that was conducted by Ziwei Chen and also a visiting scholar, Yusuke Ioto from Japan. And they were also joined by Hilary Nguyen, who was an undergraduate student at UC Irvine. And Hilary is now pursuing her PhD studies with Andy McNally at Colorado State. So this was the basic question. And my role on this, besides was feeding the students, was sort of just to ask them, how is your enantioselectivity doing? And so this was a really exciting find for us when Ziwei and Yusuke found that we could combine this adamantylamine, this very bulky amine, with this DTMM seg-phos derivative. And this allows us to perform now a dynamic kinetic resolution of aldehydes, generating these cyclopentanones with very good diastereo control, so greater than 20:1 in many cases, and good enantioselectivity. And so we believe that this amine and rhodium sort of play a dual role in promoting the epimerization. Because of the bulkiness of both components, they also don't self-quench. And so there also might be a frustrated Lewis pair sort of concept in this chemistry. If we do tune the ligand and switch to JOSPO phos, this is a ligand developed by Solvius, we see here that we can also vary the the substituent of the beta position and incorporate a wide range of aromatic groups as well. So right now, in terms of where our group's going with this chemistry, we are excited in using aldehydes in racemic form and using DKR of these substrates. We're also very interested in developing intermolecular versions where we can couple the aldehydes to olefin components and generate remote 1,4 stereochemistry. Okay, so I think that's mostly what I wanted to say about hydroacylation. I'm going to sort of acknowledge the people who voted for the other topics, maybe by just jumping to the end here. So yeah, thanks to those of you who voted for hydrogenation. My group recently, because of the pandemic, spent some time writing perspective articles. And so Patrick Parker and Sintong Hu from my lab wrote an article that summarizes our group's interest in hydrogenation. And so the main point of that article really is to argue that I think hydrogenation is still a really exciting field of research. There's a lot of opportunities, especially to develop more sustainable catalysts. One of the things we've been interested in doing is making lactones, amines, chiral benzylic stereocenters, and even chiral sulfoxides. And we achieve this by using the hydrogenation in tandem with other transformations. And so ranging from transfer hydrogenations to epimerizations, to organocatalysts, to sigmatropic rearrangements. Yeah, so if you voted for this topic, please check out Patrick and Sintong's perspective article. In the area of hydrofunctionalization, which I think won the silver medal for today's vote, I guess I'll just summarize in this one slide. One of the things that I think is really interesting is the use of dienes as building blocks, right? Dienes are typically, right, building blocks for making polymers and plastics, and we know that has had a huge influence in the products that we use. And so Mike Crochet's lab at UT Austin has shown that dienes can also be used with ruthenium or iridium hydrides to generate nucleophilic pi-allyl intermediates. And these will react with aldehydes, and the Crochet lab has shown that this can be a very useful method for natural product total synthesis, especially their group has made a wide range of polyketides. And so what we were wondering was, could we use very similar kinds of building blocks, but use rhodium hydrides? This would generate electrophilic pi-allyl intermediates. And then with that, we imagined that we could engage a wide range of nucleophiles and make carbon-carbon, carbon-nitrogen, carbon-oxygen, carbon-phosphorus, and carbon-sulfur bonds. And so I'll highlight here that this idea is feasible, and we have some initial results in this area. This was a project that was really initiated by Xiaowei Yang, a postdoctoral fellow in my lab, and she is now just starting her independent career in China as a professor. So we're really excited for Xiaowei. Okay, so I'm going to sort of summarize it. I know there's a lot of students out there who are also thinking about future work and careers and trying to wrap up PhDs. And sometimes it can be a bit frustrating knowing, what's going to be happening with these projects. But at the end of the day, really, we can tell a nice story when we look back on things, but my group's really fundamentally just interested in new chemical reactivity. Right, we like to mix things together and to see what happens. And we really rely on our friends in industry to reach out for collaborations and to share what they feel are interesting directions in the area. This is a picture of my son who just recently turned 5, celebrating Apollo Day. And this is a quote from an aerospace engineer saying, "Basic research is what I'm doing when I don't know what I'm doing, but ultimately this can lead to really powerful and practical applications." So I guess some examples of our industrial collaborations, we've had a chance to work with Givaudan. This is a company that makes fragrance. And so in terms of the agriculture and fragrance industry, this is where all the atoms really do matter. And so I think hydroacylation is a really interesting way to make ketones. And I would encourage you to join the area if you're interested in opportunities to develop much more robust and sustainable catalysts, because this is not yet a solved problem. We also had a chance to work a bit with AbbVie. Our group had developed a metal catalyzed method to functionalize sugars. And so Stephen Wittenberg challenged us with this sort of sugar, could we selectively benzylate this? Because that would ultimately lead to, I think, a really important molecule that they would love to give away for free for treating orphan diseases, such as river blindness and elephantitis. Okay, so I had a chance to talk a little bit about those. I think I'm gonna kind of end here with just thanking my research team. So these students have been a really great group of students to go through the pandemic with, and they've worked really hard. And it's just really an honor to be able to share their recent results with all of you today. I also want to end by thanking our collaborators and funding agencies. Our group's really interested in organic synthesis and also potential applications and collaborations with friends who need designer molecules. And so also one of the most important slides is to thank here all the alumni and students. I've highlighted some of my Vietnamese students in red, and hopefully I'll reach out to them to make sure they know about the VCA and have an opportunity to join our organization. And so with that, I guess I'll just say thank you to everyone today for joining, from making time in your schedule. I would be happy to answer any questions, and I hope you all stay safe and healthy, and good luck with your future work. Thanks very much.
Thank you, Professor V, for the very insightful talk. It really reminds me of the good old day when I was still trying to be a organic chemist when I was in my undergrad. Dear audience, if you have a question for Professor V, please send us those questions via the comment function on Facebook or on the Zoom chat right here, or you can even raise your hand and turn on your video to ask directly Professor V here. So with that, I guess we can start with the first question here. This is a question from Jinyan over here. So I think there's one reaction, one session where you were mentioning the nature of the counter ions, and there's one reaction that gives the best result compared to others, 99% and 99 to 1 ratio of the DR. I think it's benzonate, and Nhan was wondering why this gives the best results.
Yeah, Nhan, thanks a lot for the question. It's a really good question. We did explore the mechanism of this transformation in detail. And what we believe is happening is that the benzoate acts as a shuttle. So in this step, when we generate the rhodium hydride, with the benzoate ligand in this position, let me highlight that. It can act to shuttle the rhodium hydride. So a reductive elimination occurs to form benzoic acid, and then that leads to deinsertion to generate carbon monoxide. And so just that step of that reductive elimination that's now possible because of the benzoate, we then funnel through to a completely different pathway than people had seen previously. So you can imagine that if you have a very non-coordinating counterion, you won't get to that same rhodium acyl intermediate, right? That reductive elimination doesn't happen. So the benzoic acid acts as a shuttle and it can come back in the catalytic cycle. This whole cycle is basically symmetric. It's an equilibrium process. And so on one hand, you have like the extrusion of CO and H2. And then on the other hand, it basically gets re-added into this alkene component. And it's an equilibrium, but it's all driven by the release of strain here. So does that answer your question?
Yes, it's very clear. Thank you.
Yeah, sure. Thank you for the question.
Thanks, Professor V. There's another question this is Nguyen Duan from Facebook. This person says, hi V, thanks a lot for the wonderful talk. I have one question. Since you mentioned the molecular shuttling work of Bill Morandi, what do you think of the prospect of using a cascade of aldehyde transposition hydroacylation? Let's say we have an aldehyde alkene substrate. We can do the decarbonylation process to transpose the aldehyde through a hydroformation process. But instead of stopping at a new aldehyde, we can further use it for an intermolecular hydroacylation process. So do you have any comments on this, V?
Yeah, thanks a lot, Nguyen, for your comment and your very cool idea. I think there are lots of kind of cool creative things, and you're showing an example of some of the things you can start to think about doing, right? Suggesting like, can you move the aldehyde to a different position and then have that engage in a hydroacylation? There is work by, I think, Professor Mori, where he kind of shows the use of aldehydes. They can act as equivalents for carbon monoxide and H2, or a lot of different groups have been interested in sort of that general idea of like a hydroformylation with aldehydes as the starting input. And so I think it's an interesting idea. I think there's a lot of potential. We have thought about things like that. One of the challenges is that sometimes the catalysts that are really good at hydroformylation. And so I guess if we think about this analogy that I talked about early on, the analogy between these two transformations, one of the challenges is that the hydroformylation tends to use metal carbonyl complexes, so these CO complexes, and those catalysts are not so great for hydroacylation. But I think it is possible to think about doing things like that. And one avenue could be to use tandem catalysis or cascade catalysis, where you have multiple catalysts in the same reaction pot that are compatible with each other. CO can also sometimes be a really good ligand, and so you have to also make sure that you avoid poisoning your hydroacylation catalyst. So yeah, it's a cool suggestion. I think something definitely worth thinking more about, but hopefully I just kind of highlighted some of the challenges in doing that kind of cascade.
Thank you, Professor. There's one more question from Facebook from Nguyễn Dương, and I'm not sure you would have time to talk about this, but this person is saying that he's very curious about your collaboration works and was wondering if you can share some interesting collaborative research.
Yeah, sure. So I guess I talked a little bit about some of the friends in industry who have just reached out to more share with us the kinds of challenges and problems that might be of interest. But in terms of our group right now, the various collaborations, we do have collaborations, for example, with our theoretical chemists. So Philip Furka is one of my colleagues at UC Irvine. And so we're really interested in combining computational work and experimental work to better understand these organometallic transformations. We also have a collaboration with one of my former students, Charles Young, who's at Merck at the Boston site. And so we're sort of developing new transformations, and then Charles is helping us find applications in medicinal chemistry, especially for methods that involve biosteers for certain types of structures. And then we have a collaboration right now, this one here, this is an image taken by my colleague, Xiao Yushi. So she is a microscopist, but through working with her, we've been developing linkers, and so chemical linkers that have different types of function, and hopefully will allow us to image the cell in 3 dimensions. So we'll get information about not only where certain proteins are, but their mass and things like that, but also sort of spatially where they're located. And so, yeah, those are some of the collaborations I've highlighted here. But yeah, feel free to reach out if you have more questions, or if you want to collaborate. We're always very interested in learning more about the kinds of challenges that people are thinking about and where organic chemistry might make an impact.
Thank you, V. These are very cool collaborations. It's just for my own curiosity. What role can machine learning play in organic synthesis, and for example, how advanced it is at this point?
Yeah, that's a great question. And that's something that I think is a growing and emerging field. Charles is very interested in that area. And so we've been kind of chatting with him about it, but there's a lot of great chemists kind of around the world who's leading the way. I guess if you're interested, the work of Abby Doyle comes to mind immediately. But one of the ways that people are interested in using machine learning is to try to figure out if there are certain patterns, for predicting like the best conditions, right? For example, if you're going to perform a transformation, if you had all the data on the different catalysts that have been tried, the different solvents, and the different parameters and what their yields were, you might be able to ask the machine to see a pattern that you wouldn't be able to recognize just because the data is so vast, but then it could predict for you, for your structure, what the best conditions might be, for example. I think there's also opportunities in catalysis, all right, because with ligand designs and things like that, because sometimes it's not so obvious. I think there's also been some use of it in biocatalysis. Francis Arnold has published some work. And so I think in that arena, you've got a lot of data, right, with enzymes, and then trying to figure out how these, their primary and secondary structures and tertiary structures really influence reactivity. And so those are just some of the things to come in mind. And I think there's probably even more opportunities. It's just an area that I think we appreciate, especially when you have a lot of data. There's some opportunities there to use it in a way that we can't simply do as humans. We can use the machines to help us sort through it all. Yeah, but I don't know if that answers your question, but
it definitely does. I think the machine learning right now is playing such a big role in everything. When it first emerged back then, I never thought that it could be applied to organic chemistry. But right now, obviously, it's helping organic chemists in ways that we couldn't imagine back then.
Yeah. And I think, one of the challenges is, making sure that the data is consistent, right? Because we all sort of run experiments and we often don't report the things that don't work or that are low yielding. And so I think it would be an interesting opportunity for the field to actually share more data, right, on what we know works and what doesn't work, and how to make sure it's standardized in some ways.
Right, right. We have a question from Van. Oh, I know Van. She used to be a visit. She used to visit UCSB at the time, but I think she made this decision to join USC for a PhD instead. Van has a question. So she's saying that she's working with Dr. Travis Williams at USC. With the metal-hydride transfer catalysis, and they have recently noticed that some their active catalytic species are carbonylated metal species. Just out of curiosity, have you observed anything like that in any of your mechanistic studies where metal CO isn't poisoning your catalytic system?
Hi, Van. Yeah, thanks for the question. So it's a really interesting question about, if I understand it correctly, how carbonyl complexes are typically thought of as poisons, right? They're inactive, and it's a problem usually when you generate CO because it's such a strong ligand. And it can be hard to reverse that process. So one of the things that we found, highlighted here. Okay, so if you can see my slide here, in this case, we do see carbon monoxide formation, and I do believe that the carbon monoxide can coordinate to the metal, but my feeling is that these acrylamides can sort of act as hemilabile or bidentate ligands, and maybe that extra coordination helps extrude the carbon monoxide, especially at these elevated temperatures. And so in terms of metal carbonyl complexes, I do think it's possible for them to be catalytic if you have the right ligand coordination, and especially if you're operating at higher temperatures, that CO can be reversibly bound. But it definitely can be tricky sometimes to get the catalysis. Of course, certain types of transformations really aren't impacted by that, right? Like there's a lot of metal carbonyl chemistry where you can just use the metal carbonyls as catalysts themselves. And so I guess long story short, it really depends on what you're trying to do. But I do believe that even in some cases where you're generating carbon monoxide, it is possible to do catalytic chemistry. And this is how decarbonylation works, right? Or yeah, I think decarbonylation would be sort of the most relevant one. And so if you're looking for ways to overcome CO in your reaction, I might take a look at Eric Carrera has a nice catalyst system that allows for catalytic decarbonylation of aldehydes. And so looking at his ligand design, it might kind of give you some ideas on how to overcome that.
Thank you, Vi, for a very detailed response. Kim Nguyen from Facebook has a question about, so basically there are a lot of chemistries that you're presenting here, but they have not had industrial application yet. So can you share what are the challenges that need to be overcome in order to use these chemistries at the industrial scale?
Yeah, I think that's a really good question. And when you look at transformations like olefin metathesis or asymmetric hydrogenation, there have been a lot of people, or even cross-coupling, right? There have been a lot of people working on these areas for a long time, and a lot of better ligands develop, better metals, and better mechanistic understanding. And so in some ways, I think hydroacylation is just a younger area of research. I think that a lot of the features of the transformation are attractive, and mainly it would require really, to some extent, understanding exactly what you're putting into your reaction. So one thing we found so far in terms of lowering catalyst loading, when we generate our active catalysts by just throwing in the ligand, the phosphine, the precursors, and mixing everything together, sometimes disproportionations can happen where you form a rhodium complex that's inactive. And so that results in higher catalyst loadings that would be ideal for industry. So in my mind, I think that the industrial applications are possible. It might be, developing more robust catalysts so that our friends in industry, when they do think of, making a ketone, and if they need to make one, they have like a really, robust set of ligands and catalysts that they can go to. Right now, I would say like every hydroacylation is kind of different. It's a different ligand, it's a different counterion, sometimes a different metal. And so that might be one of the reasons why people are hesitant, because it's just almost looks like there's so many parameters to test out at the end of the day. At the same time, I would argue that there's no real universal catalyst for anything, not even for a palladium catalyzed cross coupling, right? And so, yeah, in terms of why, it's a good question. I think at the end of the day, I would say it's a mix. The chemistry needs to be better developed, and at the same time, maybe more awareness from our friends in industry, because I do think that the resources are there with industrial researchers, that if they did commit to saying, hey, we really want to make this product using, this aldehyde and this olefin, I really think that they would be able to fully screen the parameters and get there.
Thank you, V. And again, from the audience here from Zoom, we've always talked about, we don't have enough engagement from the Zoom participants. So if you have questions, so please feel free to jump in, raise your hand, turn on your video, give us some signal so that we know that you have a question for our guest speaker here. So from Terence Thang Nguyen, he's asking, oh, do you want to ask him ask our guest speaker directly, Terence?
Yeah. Hi, V. That was a great talk. So I was wondering, so I came in late, so I might have missed this, but I was wondering about your rhodium catalysis. So you might know about the price of rhodium. It's increasing to 17K per ounce. So I was just wondering if there's like any other metals that your group has explored that has the same reactivity and selectivity as a rhodium in your system.
Okay. Yeah.
Or in the audience, also Nguyen Duan has the same question about rhodium price. Is it taken into account when using it on the industrial scale compared to palladium and stuff like that? So it seems like this is a very famous problem in organic synthesis.
Yeah, thanks so much for talking about that. It's good to meet you, Terence. Hope things are going well in the Davies group at Emory. And I know Hugh's group is also really interested in rhodium catalysis, right? And it has sort of like a unique role. So our lab has looked at other metals, and we are, fundamentally very interested in all transition metals, to be fair, because we really are more of an organic group in terms of the way we look at the periodic table. Everything looks like a parameter to be explored. I would argue that, in the beginning, we've looked at a lot of rhodium because there are so many great phosphine ligands that have been developed for rhodium. And so when we think of a new variant that we want to test out or try, I think my students can have success by sort of going through the phosphine libraries of available ligands. But cobalt is doing very similar things. There's been papers from our lab and other groups where you can almost do the analogous reaction. So the ketone hydroacylation that we published, a group later on, I think it was the Yosakai group from Japan, they published pretty much the same substrates, but with cobalt as the catalyst. And so, it's possible those mechanisms are a little bit different, just like Paul Sherrick has shown that cobalt hydrogenations, even though they look kind of similar, they have very different mechanisms to rhodium. So there's more of a one electron pathway instead of oxidative pathways. But yeah, to answer your question, for sure, I think that it's possible to use other metals. Cobalt, nickel are good candidates for this kind of reactivity. And our group's also very interested in looking at that. I think it also depends on just so where you are, like if you're kind of developing new chemistry, maybe we're not so concerned at the beginning of what metal we're using because it's like a new transformation that we're trying to look at or a new concept we're trying to explore. But at the end of the day, I think that different metals, not only because of the cheapness, but they just offer new reactivity. So they're worth exploring from that perspective. Yeah, and there was another question about, what about rhodium in industry? I've talked to friends in industry about this question. It's kind of interesting because rhodium in industry like, especially in the agricultural industry, it's really embedded. And so they have really great ways of using the rhodium, of recovering it, of recycling it. And so they're probably a little bit more hesitant to try a different metal and, you know, like a different hydrogenation, because then you kind of have to rework that infrastructure, right? They probably already own a lot of rhodium and, you know, can do these processes on very, very large scale. And so I think that, you know, especially for big industries, right, like agriculture or, you know, the petroleum industry, it's slower to change processes, right? You've already bought that giant reactor that does that hydrogenation well, and you know how to do it. And so it's a good question. I think that, you know, it really depends on the industry, but rhodium, I don't think it's a problem actually right now. Maybe in the future, maybe if we don't sort of find other ways to get the rhodium, but basically, I do think, you know, other metals are cool. And you probably know, Terrence, that, but rhodium is also pretty unique, right, in its reactivity. And so I don't think it's sort of a question of like, can you just replace it completely in all cases?
Thank you so much, V. It was nice meeting you.
Yeah, good to meet you. Say hi to Hugh for me.
Thanks, Terrence, for the question and V for the very detailed answer. So I think everybody, if no one has any question, I would like to have a question for Professor V. So, you know, I'm also doing quite fundamental work. You know, biophysics is obviously something completely different from this, but it's still fundamental research. And how do you find the motivation to, you know, persevere on this arduous journey when, for example, in order to turn your research into something that have an industrial application, it is still a long way to go. So how do you keep yourself captivated in these very interesting yet quite fundamental questions?
Yeah, it's a great question, kind. You know, I do think about this a lot, especially, you know, when you sort of enter a field like this, mentoring is also a big part of my role. And so one of the things I would advise is, you know, a lot of us do go into chemistry because we're initially really excited. You know, we learned that, oh, wow, this is, you know, kind of like Legos, or I can build new things and I can transform these molecules. And then once you start doing it, I think it's almost with everything kind of in life, like there's going to be that part that's kind of tedious, right? Like when you're learning how to play an instrument or learning a new sport, you've got to do the drills. And so in this case, you've got to run the control experiments and do the chromatography and get the bad results and try new things. And so I think in some cases, embracing the idea that, you know, we are sort of collectively working together to make progress, right? It's not up to any one person necessarily, but kind of like getting better at that skill set, right? And it's sort of like you have this lifetime opportunity to develop new things and work on your ideas. And so I feel like it keeps me motivated to realize that it's okay to not be motivated. It's okay to be bored. It's okay to find the work very tedious at times. That's actually going to be a normal part of the process, like of being a scientist, right? That things aren't going to work most of the time. And then when they do work, to really step back and celebrate those moments with your team, because those are like really, really important moments. And so when we get high enantioselectivity, or when somebody publishes a paper, or you know, even little things like when my students run their very first experiment in graduate school and get their first yield, you know, we'll celebrate those accomplishments. And so, yeah, I hope that makes sense. But I think a mix of realizing it's okay to be bored of your stuff, that's actually a normal thing, but you got to just kind of keep going and realize that you're making a bigger picture impact, right, at the end of the day.
That's quite a healthy philosophy and environment that you have there in your lab, V. And I think your students would really appreciate that from you.
Thanks.
So if no one has any further question for Professor V, I would like to end the Q&A session now. And again, I'm saying this for everyone. Thank you so much for for what you bring to us today, V. Essentially, it's really our honor to have you here today, and it was such a great talk, and that I can feel like everyone here today has benefited from what you're sharing, from the conception research of an enantioselective hydrofunctionalization. And I think every researcher wants to have such a kind of research with high impacts in this area. We have learned a lot from you today, and we hope that everyone likes this webinar today, and continues to contribute to the same program, so that we can develop our group for Vietnamese people in general in the future. So before ending, would you please send us some message for young chemists and scientists for their career and their choice in life, Professor Ree?
Yeah, I think for young scientists, for young chemists, for your career in life, my advice would be to read a lot and stay positive, right? I think being positive is really important. Just kind of like sometimes stepping back and seeing at the end in the day, we're really fortunate to be doing chemistry. And I think reading is important because, we all kind of come from different backgrounds and different areas, have different opportunities. But when you pick up a journal or pick up a book, you have access to the same experts that anyone does. And so through reading, you really have access to mentors from all over the world, right? And so that would be my advice. Read a lot and stay positive. You have your entire futures ahead of you. And so we're really relying on you guys to make this place a better world through chemistry.
Thank you, V, for the advice. So after this webinar, we'll send out a feedback form for everyone to fill in, and with any comments, so that we can improve our program here. So we really appreciate that. We'll also post a video recording of this webinar on YouTube for you to access. And once again, thank you so much, Professor V, and thank you everyone for joining today. We hope that you have a great weekend, and I hope to see you guys soon.
Thank you, Professor Lee.